All right. Well, welcome everybody back to the second talk now of the discrete optimization talks. And I'm very happy to have Andres here. Could you go in full screen? Perfect. Andres, he recently joined the USC as an assistant professor, and he is very talented at many different things, mixed-integer programming and convex optimization. I constantly check his site monthly for new updates on his research, and there's always new things that he's working on that I never heard about, grants that he's winning. And so I'm very happy that he accepted our invitation to be here. Please take it away, Andres.
Okay, so thank you very much for the nice introduction, and thank you to Alec and Elias for organizing these talks. I think you've done an amazing job at bringing us together. So today I will talk about outlier detection problems in time series. So roughly, here is a quick overview of the problem we're trying to solve. We have a Wiener process or Brownian motion, WT, that is kind of evolving over time. And we're not able to see this problem, this process directly, but instead we see some noisy observations. I'm not sure if you're able to see them on the graph, like in blue crosses. And given these noisy observations, we would like to recover the actual values of the process. And so eventually find an estimator that perhaps would look like this. I'm going to call this X. And this problem, as just stated, is actually a very easy problem. It turns out that perhaps standard way to solve it is using maximum a posteriori estimation, where we solve the optimization problem on the board, where we try to find this estimation X that maximizes this joint probability, where the first term, W equals X, is just stating that what we predict, X, should possibly be generated from a Wiener process. And the second term says that given this prediction, the observations that we're seeing are likely to be generated from these noisy observations from what we predict. And this process, after taking logarithms, negating, and some transformations, reduces to a simple looking convex QP, where we get essentially two forms of terms. We have the first summation in here that imposes smoothness between consecutive terms corresponding to this distribution of a Wiener process. And the second term penalizes how far we deviate from the actual observations. So it's very easy to solve. I just showed you before like what it would look like. And so that's a clean, nice problem that it's not the main focus. But here we're going to look at the version where this process is corrupted by outliers. So again, so we have now here some red dots all over the place, which are kind of grossly corrupted observations. The process itself is the same, but now we have these points that are completely far off. And if we try to just fit a maximum a posteriori estimate without accounting for these outliers, then we're going to find something that really tries to capture or fit the outliers, and the performance is of course going to be very bad in this setting. So the idea or the problem that we're going to look at is try to correct this maximum a posteriori estimate as follows. So first we're going to define some set calligraphic Z, which is some form of prior or some constraints that we know on the outliers. And for the sake of this talk, you might think just as an upper bound that we know we have a maximum, a given number of outliers. And we have this set S that has to belong to this, satisfy this constraint. This is going to be a decision variable. And this is going to be our estimation of which points are actually outliers or not. And so to map estimate, in addition to picking X according to a possible distribution of the Wiener process, so we're going to select a set S, and we're going to update the second term in this probability, where we only care that points that we think are not outliers kind of correspond well to this prediction that we're making X. And for the terms that are outliers, these are simply discarded because they're nonsense. So we don't need to worry about those. And this turns out to reduce to some simple looking, perhaps, quadratic program, mixed-integer quadratic program. So here we're going to have some binary variables Z, which are one if and only if a given point is estimated to be an outlier. And we have these additional variables v that account for some form of correction factor, if you want, or help us discard points. So the idea here, if z is 0, then to become constraints here, indicator constraints, force v to be 0. And this term reduces to what we had before. It's just this error between what we observe and what we predict. On the other hand, if z is 1 and we predict that this point is an outlier, so v can take any value. And so it doesn't matter what we predict here for x, because no matter what prediction is, we can just pick v that will make this whole term become 0. So that point becomes discarded effectively. And that's what would happen on this example that we're running. So kind of the outliers are put aside. Of course, in this example, they were very easy to identify. And we get a good prediction of the underlying process. And I would like to point to two things, kind of going back a little bit to the literature and to previous approaches, is the problem as formulated here is a variant of the least stream squares problem, which is a well-established problem in statistics. And it has been studied, at least from the theoretical perspective, because it happens to be quite challenging. But for example, it is known that it is a more robust estimator that the usual approach where we replace the square terms with the absolute value, because the absolute value is less sensitive. So this version is actually tends to be much more robust and perhaps better if we have data that is really grossly corrupted. And there have been some mathematical programming approaches or studies concerning this least stream squares problem. And in fact, the formulation that I presented before is very closely related, or it's equivalent actually to this formulation of Ziotis and Avramadis in 2005. So there have been studies, both from statistical, like theoretical perspective, and in mathematical programming approaches of this form of problems. So before jumping a little bit into the optimization, let me digress a little bit. So in practice, what people tend to do, so that they don't usually just pick the MIP solver and throw it, but they have kind of more heuristic approaches of that work along the lines of you fit the process with the outliers, you pick perhaps a data point that is most apart, let's say, from this estimation, and you discard it, you fit again, and you repeat this process until some convergence criterion or every data point looks reasonable. So mixed integer optimization, on the one hand, by solving this problem to optimality would give us better predictions, or so we hope. But I want to emphasize here another point is that it offers so much flexibility thanks to the modeling power of MIP. And so here is a specific example with forecasting. So in forecasting, we no longer care about the actual value of this underlying process, but we want to predict the next variable like yi, given all the previous data. So it turns out that under these conditions and with no outliers, exponential smoothing is in some sense the best that you can do. So we can adapt it as follows. So now instead of discarding points as outliers, we are going to correct the value of a point to some other value that in some sense results in the best fit. So conceptually, we're going to think of the observation, that's a constant, plus this auxiliary variable as the value of the corrected value for yi. So this is not a new variable, this is just renaming. So we can simply add these constraints stating that each prediction that we make is a convex combination between the previous prediction and the previous observation. And this is essentially what exponential smoothing is doing. And you get now a method that corrects values of outliers. And I mean, it's a little bit small, but you see here in black what the corrected values are. And these values are not necessarily the trivial value, which is right where you predict, but it can be less or more, such that the overall predictions are better. And so it's a much more perhaps informed way of handling outliers when you have a forecasting goal in mind, that perhaps one of the simple approaches. And just like that, so there are many kind of simple modifications that we can do in this core problem. For example, we can add constraints to really look for outliers that are clustered together. And this is a setting where this one at a time discarding of a point tend to do bad. And we can do isotonic regression. We can do pairwise Markov random fields. This is no longer necessarily a one-dimensional problem. So thanks to MIP, in some sense, if we're able to come with a reasonable approach for this problem, we're now killing a lot of birds with one stone. So that is a very attractive of MIP. So let me move away a little bit from the statistical problem and perhaps work on what we're more concerned about, and it's how we're going to MIP this problem out. So that's exactly what we're going to do. So this is Gurobi with a 30-minute time limit. Everything is modeled in Ample and solved in NEOS. And so here is some examples of what happens when trying to solve this quadratic programming formulation in a problem with 100 variables. It takes on average 10 minutes. In this case of the 5 answers, 4 are solved to optimality. The gap is low. So this perhaps might look like a good performance or a reasonable performance. But as we increase the dimension, we start to see suddenly these very large end gaps popping up after 30 minutes that get worse and worse as we increase the dimension. So very, very quickly, we're left off with these problems where essentially we have 100 optimality gap. And MIP is doing, let's say, not a good job. I should point out that the feasible solutions found are actually not bad, but the lower bounds are really, really bad. And so it's hard at this point to argue perhaps, I mean, I wouldn't call this a success story, at least using this formulation. So let's try something else. Since we have a problem that is a combinatorial problem, it's hard to solve. We can do what is actually often used in statistics and machine learning is we try to find some convex approximation. And we solve that instead of just solving the MIP, and perhaps we just use directly the solution from the continuous approximation, which is all fast. Or perhaps we round it somehow. And so here the relaxation is we just remove integrality constraints on the indicator variables. And on the example that I showed you before, here is the estimator that we would obtain. And essentially we predict 0 all the time. And when we look at the values, every single data point is treated as an outlier and is discarded. So this is a continuous relaxation. It couldn't be worse. It's completely uninformative. It will be very hard to round. I mean, it's not surprise that branch and bound is working bad if he's working with this continuous relaxation, because it's very hard to get any insight from a solution that just decides to discard every point and predict 0 throughout. So this is looking pretty grim. So let's keep going. So we cannot MIP it, so we cannot use the convex relaxation or the natural. We can try to convexify it, and that's perhaps going to be the main focus now. So here is my nice MIP, or not so nice apparently. And so we have this behavior, quadratic optimization. We have indicator variables, so binary and this variable that is on and off. So the state of the art for this class of problems is the perspective reformulation that essentially calls for looking for the continuous variables vi squared, and we just replace it with vi squared divided by zi, which is ideal for this separable term. The issue is that we don't see in this problem any separable vi squared terms lying around waiting to be kind of perspectivized. So we cannot really apply the perspective reformulation in this setting. But that's fine. I mean, there are other things that we can try. So the next thing to try is to try to look at a simple, not necessarily one-dimensional, but a simple rank 1 quadratic term. Often convexifying this is not too difficult. So we have 2 forms of rank 1 quadratic terms in here. And the first one is the smoothness terms. But this is just continuous variables throughout. There is no discrete variable at all. So that's already convex and perfect. So the second term is these error terms. So now it's a little bit more interesting. We have kind of this combination of V, which is continuous, but is controlled by this indicator variable, and X, which is just continuous. So now we have a starting point, and we can try to convexify based on these rank 1 terms. But then it's not too hard to prove that there is nothing there. In some sense, that is already a good formulation, what we have in there. And so we cannot strengthen basing on this rank 1 strengthening. And So at this point, perhaps we should be a little bit scared because now we're running out of things to try, and this is looking worse. So that's something I found as a small digression. Very interesting about statistical problems is they're very different compared to perhaps usual operations research problems. And you get these formulations that is just 2 lines, not 2 pages, not 1 page, just 2 lines, where everything looks nice. When you look at every individual thing and everything, that there is not like any obvious, I mean, there are big ends, sure, but that there is no obvious like naive formulation, and yet the relaxations are horrible. So what we're going to do, and so this is the main theorem or the main result, is now we're going to, since we couldn't deal with the rank ones, we're going to try to understand this rank 3 quadratic term. And so this is what's happening with 2 consecutive points. So we have a first term, essentially corresponding to how this point differs from a given observation. The smoothness terms corresponding to this point and the next, just 2 continuous variables, linking together kind of these 2 additional terms, and then again the error of the second term. And we're going to look at this as a whole, and so we were able to prove an ideal formulation. That looks a little bit complicated. I would come back to this formulation and try to provide some intuition later on. I want to point out 2 very quick things. So here we're using additional variables W and Z. But these are variables that are defined via inequality constraints, or in the case of Z, kind of very simple inequality constraint. So they're very easy to just replace and project out. So this is really a convex Hall description in the original space of variables. And the second term is, we have here a term which is squared divided by linear. So that's easy to represent in using conic quadratic optimization. And every other term in this formulation is either quadratic or linear. So this is a conic quadratic representable set, and that's something that we can use with many solvers, Cplex, Gurobi, Mosaic, for example. And so we're in good shape. And here, I'm not going to show how the whole formulation looks like once this convexification is applied, but it's simple in the sense that there are no callbacks, that there is no cuts, no nastiness. We just formulate it, and that goes straight into ample, and then that goes straight into NEOS. And here will be the solution that we get just from the continuous relaxation, this strong continuous relaxation on this problem. So this is not the optimal solution, but we could be mistaken on thinking that it is. I mean, it looks pretty reasonable to me. So it's not optimal. The optimal solution actually looks like this. So there is this very small differences in a couple of data points, but we're really in the ballpark. And by using this formulation, we go back to this, mapping it as we wanted. And now we see some perhaps dramatic improvements for problems with 100 variables. It's solved in 3 seconds to optimality. We go from requiring like 6 million nodes to 2,000 nodes. When we go to 200 variables, now we go to 75% optimality gap to solve in under 2 minutes to optimality in all cases. In 500, so at some point we're going to hit something that we cannot solve to optimality. That's perhaps normal, but we went from this close to 100% optimality gap to perhaps a very respectable 13%. And I should point out that most of it, so the actual root gap of the kind of the strong relaxation is 16%. So most of it happened in a couple of seconds at the root node, and after branching for 30 minutes, we were able to close these additional 3 points. But most of it is literally the strength of the continuous relaxation that is working. So perhaps going back to this statistical intuition, perhaps if this relaxation is so strong, perhaps that is enough. Perhaps we don't need to go and solve some MIP, but we can just solve the continuous relaxation and use it as an estimator. So that's what we're going to see next. First, before the results, going to give a little bit more intuition into how the instances actually look like that we're testing. So we have three types of instances. In the first one, we have outliers that are on average 3 standard deviations apart from the true process. And so you can see here that they're apart, but sometimes they land close or right in the process. Another one, outliers are 15 deviations, standard deviations apart. So note that they are really apart from the process. And in the third setting, they're kind of independent. So they're no longer centered around the process, but they're just kind of all over the place, including, again, some cases where they happen to land like right close to the actual process. And so here are kind of the results. So this is no longer optimization. So here it's a little bit more uncomfortable where for an optimizer, at least, we're evaluating how good we're able to predict this underlying process, which is not directly related to the actual objective function that we're optimizing. But we see that things look pretty nice. So the natural relaxation is of course the worst one. And depending on the instance, it can be very bad or slightly bad, but it's always the worst. And we see that by this convexification, just solving the continuous relaxation gets us an error in the order of 2%. So 0 will be the best. And this happens in seconds. And so that perhaps is pretty good. And it's actually close to what we would get if we solve it to optimality. That if we were to solve this to optimality, we actually get around 1.7 instead of 2%. So the main takeaway here is depending what you want to conclude. If you want to conclude that MIP is good, then yes, there is value of actually solving this problem to optimality. But if you were looking for something that was very fast, then we can get very close to this optimal solution by just solving a continuous optimization problem. So that's kind of the big overall results. And I'm going to try to spend a couple of slides to look at the theory on how this convexification was derived, and to try to give now some intuition about this reformulation. And so how do we convexify some sets involving nonlinear functions? I would say right now the state of the art is disjunctive programming, because it's kind of very general and it always works if we're able to go through all the steps. So here I'm going to describe an alternative that is kind of using lifting that is equally general. So this also you can work for any problem, but I argue that in some cases this might be a better approach than disjunctive programming, or an easier approach, let's say. And the theory itself, there's this very nice paper by JP and Mohit. Where they expose kind of the theory, and they have sequence independent lifting and generalize essentially the lifting from linear optimization to the nonlinear case. I'm not going to go into the full generality because it's, at least for this problem, not needed. But so here is the magic formula. We have a function g, has some discrete, some continuous variables. This can be anything, and we want to find the convex envelope of this function. So the main idea is certainly for any point belonging to the set X, if we subtract alpha transpose X of the two sides of this inequality that is defining the set, we haven't done anything. So that is valid. We can find a lower bound on the right-hand side by projecting out variables, the continuous variables. So just by minimization. And so we're left with this discrete function or set function G alpha of Z. That is very likely non-convex. And we can always find another lower bound just by picking the convex envelope of this possibly non-convex function, discrete function, G alpha of Z. So since this is a set function on binaries, this convex hull is polyhedral. So that is perhaps nice. So when we pull it back together, we have found a valid linear inequality where we add alpha transpose X to both sides, and then we found that this is always larger than this linear term, plus this convex envelope that again is piecewise linear. So you can think of these inequalities as a bunch of linear inequalities. And this process that I just outlined works no matter what this alpha vector is. So we just go and find the best alpha. So we maximize over alpha on the right-hand side. And that happens, it's a nonlinear inequality, and it actually describes the convex hull of the set. So that's the best possible. Now let's try to look it a bit on our example, how this process would look like. So we have this function g that has two continuous variables, now x and v. We have these constraints, indicator constraints. The first part is we need to project out the continuous variables. So this might look actually like a very hard problem because first, so we need to describe this function. So this function is discrete, means that we need to give a value for any possible value of z. And this could be hard, but in this community discrete optimization, perhaps we're not that scared to deal with discrete functions. In this case, it becomes very easy because there are only 4 possible values. So we need to do 4 cases, and that's it. The second part, and perhaps that is even more scary, is we need to compute this for every possible value of alpha and beta. And so there are like infinite possibilities. If you're used to working in linear optimization or mixed integer linear optimization, this very likely looks insane. Because in linear optimization, as you change alpha and beta, the solution might move from one extreme point of some polyhedron to another, changing dramatically. And so you get kind of a lot of cases. But in this nonlinear world, we have smoothness. That is something that perhaps, or at least me, I was not used to think about something important in discrete optimization. But here it works nicely because we can take derivatives set to 0, and then we can get closed form solutions thanks to this smoothness for any value of alpha and beta. And in this case, we end up with some simple formula of this function g alpha of beta is just a constant that depends on alpha and beta, but not on the variable z. Minus another non-negative constant times the maximum of z1 and z2. And so that's just taking derivatives and setting to 0 in this case. Second part is the convexification. But now we have moved from convexifying a nonlinear object that is hard to looking at some polyhedron, which is in principle easy. Now we have facets, we have a lot of theory. And in this case, the convexification of how to describe the hypograph of a maximum over binaries is essentially found in the very first few pages, often as an exercise in integer optimization textbooks. The maximum is less than 1 and it's less than 2 sum. So the intuition behind the inequalities, this is it. The only information that we're giving to solver or that we're exploiting is the fact that the maximum is less than 1 and the maximum is less than 2 sum. And the next step, we need to solve this lifting problem, where now we need to find the best inequality, alpha and beta, after convexification. In this particular case, this happened to be a convex optimization problem. So perhaps we were lucky, or perhaps, I mean, I know this is not always the case. There are problems where you won't get it. But I think on a surprising amount of problems, you'll just find convex optimization problems and take the derivative, set to 0, and solve. And you get an explicit formulation as I shown you last. So my next slide, here is a recap, and the paper is available in Optimization Online. So thank you very much.
Thank you, Andres. That was a very great talk. Actually, thank you to both of the talks. They were both very awesome. I was very happy with them. I have questions for you. I have questions for Weijen. In the interest of time, let's cut straight to the breakout rooms, and then people can ask Andres question in breakout room 2, and Weijen will have breakout room 1. Thank you everybody for coming, however, in any case. And also, if you have questions and you don't have time to ask them now, you are welcome to use our Discord channel, and there you can ask them asynchronously, and I will make sure to let the speakers know that there are questions waiting for them there. So anyway, thank you both very much for coming. I think next week we do not have talks, by the way, because there is IPCO, and we will resume again in 2 weeks from now. Andres, did you have something to say?
Am I still? Yeah, sorry. I was struggling to stop sharing my screen.
All right. Well, okay, so I'm stopping the recording.